Hello students of Year 10 Maths General, and welcome to this exercise 2G video which focuses on compound interest. Now before we take a look at compound interest, let's just remind ourselves about the conditions surrounding simple interest so that we can really clearly decide what are the differences between these two topics. So with simple interest, the amount of interest earned is always calculated based on a percentage of the original amount of money. So that's the important part of that sentence, the original amount of money. So when you take out a loan or an investment under simple interest, the interest that you'll be charged is always calculated on whatever that amount of money was that you originally started with, which is what we call the principal. So here's an example. $100 is invested at 4% interest. Okay, and if this is simple interest, that means in the first year, $4 of interest will be added because 4% of $100 is $4. So after that first year, we're at $104. Okay. Now, in the second year, again, we're just referring to the original amount of money to calculate our interest. So again, we get 4% of interest on our $100 original value. So we get another $4 of interest. So now we're at $108. Then in the third year, again, the same thing happens. The interest is calculated from the original amount of money, which was 4% of $100. So again, we just get $4 worth of interest. And we end up with $112. Okay, so each year we grew by $4, the same amount every time. And that's because with simple interest, every year the interest is calculated based on a percentage of the original. So in our case, it's 4% of the principal of $100. So that what this means for us is under simple interest, the final amount of money we have grows, whether it's in a loan or an investment, but the amount of interest earned never does. Every single year we receive the same amount of interest. And this causes linear growth for our simple interest. Now let's take a look at compound interest and how the conditions are different. So under compound interest, the amount of interest earned is calculated based on a percentage of the current amount of money that is in the loan or investment. So that's the difference. With simple, it's the original amount. With compound interest, it's the current amount of money. So what that means is as the amount of money that's in the loan or the investment changes, the interest you receive will change as well. Another way of saying this is that the interest received is put into the loan or investment. So whenever you receive interest on your compound interest bank account or on a loan, that interest is put back into the loan or investment. So it grows, and that allows it to earn even more interest next time. And that's why it's called compound interest, because to compound means to add on to something. So our interest adds on to the principal, and now we're receiving interest on a higher amount of money. So let's take a look at this example down here. It says $100 is invested at 4% compound interest. So we'll say it's 4% per annum and it compounds annually. And you'll see the significance of that a little bit later when I explain. So we've got $100 invested at 4% per annum compound interest, which compounds annually. So in the first year, our principal, it hasn't changed yet, no interest has been given, but in the first year, 4% of $100 is added to our account. So $4 of interest will be added. So that brings us to $104 after the first year, just like with simple interest. Now, in the second year, this is where things become different to simple interest. In the second year, 4% of 104 is what's used to calculate our interest because our account grew to 104 at the end of the last year. Remember, with simple interest, it stayed the same. We were always calculating from the original. Now with compound, we calculate from how much money is in the account right now. And it's, like I said, it's $104 and we need 4% of that. So 4% of $104 gives us $4.16. So after that second year, we're now at $108.16. So as you can see, we're 16 cents better off than under simple interest at the moment. Now in the third year, again, we're not calculating off our original amount of money. We want 4% of $108.16. So that's 0.04 times 108.16. Which is $4.33. So now the interest received in the third year, it's not $4 like under simple interest, it's $4.33. So what that brings us to now is a total of $112.49. Alrighty, so we can see under compound interest, we are now better off by 49 cents after 3 years. That margin, however, will just continue to grow and grow and grow because the extra bit on the top, see in part two, in the second year, sorry, we were only 16 cents better off. Now we're 49 cents better off. Every single year that goes forward will be better off by an even higher amount. And the next slide will really demonstrate that for you. But let's just read this little piece of information down here before we do. So every year, the interest is calculated based on 4% of the current amount of money. That's the difference. With Simple, it was the original amount of money always, but now it's our current amount of money. So the final amount of money grows, and the amount of interest earned each time period grows as well. So under Simple, our money grew, but our interest never did. Under compound interest, our money and our interest grow, which causes even greater growth for us. So this graph here really shows that visually for us. With simple interest, we just have a straight line. So it has the constant gradient all the way along. It's increasing by the same amount of money every single year, $4 in our case. Now with compound interest though, because we increase and then the interest goes in and now we get even more interest next time period, this graph gets steeper and steeper and steeper. The further we go along, the steeper it gets. Because what that means is we're growing, but the rate at which we're growing grows as well. And we call that exponential growth. And that's the difference between simple and compound interest. Simple has a linear growth, and compound interest has an exponential growth, which is much better when it's your money being invested. Now, something that we do need to talk about before we start calculating with compound interest is this. So it's the compounding period. So like I said, compound interest is named for the process of receiving interest, which goes back into the account or loan, therefore increasing the interest received on the next time period. So your interest compounds into the loan and causes even more interest next time. We have a phrase called the compounding period, or sometimes called the rest period, and this refers to how often that process occurs. So if interest is being added into the account more often, we have more chances for our money to grow and more chances for our interest to grow. So this down the bottom here, this is a general truth about the compounding period. More frequent compounding periods equals stronger growth. And when I talk about the frequency of compounding period, like I said, it's how often money is compounded into the account. So, for example, this could be yearly, it could be once a year, or it could be monthly, or it could be weekly, or it could be any time period we could think of. But we could call it compounding monthly, or a monthly compounding period, or rest periods of 1 month. All of those different phrases refer to a monthly rest period. Let's see now how we actually calculate with compound interest and how the compounding period affects that as well. So this here is our formula for compound interest. A equals P outside of 1 plus I all to the power of n. Now what all the letters refer to here is A is the final amount. So this formula is actually calculating what is the final amount of money after interest has been added to the account over all of the years or months that we're talking about. Now the other letters will actually be quite familiar from simple interest. P is the principal, it's the starting amount of money. I is the interest rate converted to a decimal. And N is the number of time periods or number of compounding periods, sorry, that the loan goes over. So this is where compounding periods becomes important, okay, with both the letter I and the letter N. And I'll do an example that demonstrates it as well, but I'll just talk about it now too. So I is the interest rate per compounding period. So often we're given interest rates as a yearly interest rate. So for example, I might have 12% per year. But if my compounding period is monthly, I need to split that yearly interest rate into monthly interest rate by dividing by 12. And the same thing has to happen if it's weeks or fortnights. I divide by the number of them that occur per year. So my 12% interest rate per year actually represents 1% interest per month if the compounding period is monthly. And like I said as well, n is the total number of compounding periods. So in the same way, if I have a monthly compounding period and I want to do interest for 1 year, I don't put the number 1 in as n, I put the number 12 in because there'll be 12 compounding periods in the 1 year that I'm interested in. Now, just down here, this says, if I want to find out what amount of interest was earned, what I need to do is I need to take my answer from this formula here, the A value, and I subtract the initial value. So all I'm doing is I'm finding what's the difference between where I started and where I ended up. And that's what represents the amount of interest I earned. So now let's take a look at some examples. The first example, it says determine to the nearest dollar the amount of money accumulated after 3 years when $2,000 is invested at an interest rate of 8% per annum, and it compounds annually. So since it compounds annually, we don't need to change the 3 years, it's already in years. We don't need to change the 8% per annum because it's already in years as well. So this will be nice and straightforward for us. We just write our formula, A equals P outside of 1 plus I. all to the power of n. And now we start substituting our values in. So our p-value was 2,000, our principal's 2,000. Our interest rate was 8% per annum. So we convert 8% to a decimal, which is 0.08. I've divided by 100. And then my power of n, it's the number of compounding periods. And I've got 3 years with annual compounding. So that means it will happen 3 times. So now my calculator can sort the rest out for us. 2,000 outside of 1 plus 0.08, all to the power of 3. And the answer I get is $2,519.42. So that's my answer to A, which asked, determine the amount of money accumulated after 3 years. So what is the final amount? Now B says, determine to the nearest dollar the total amount of interest earned. So using the second formula from the other page, or just common sense really, the amount of interest earned is our end value, our amount, minus our starting value, our principal, because we're finding out what difference occurred over that time period. So my A value is 2519.42, and my principal, is $2,000. So clearly, without even using a calculator, our interest earned was $519.42. So let's just interpret these answers really quickly. In A, we were calculating what is the final amount of money. So someone invested $2,000 and that turned into $2,519.42. Now B is asking how much interest was earned. So here we're not looking at what amount of money does this person have at the end. We're looking at how much money did they make over that time period in interest. And that's $519.42. Alrighty, this final question, it says Courtney invests $50,000 in an account that earns interest at the rate of 4.5% per annum, but it compounds monthly. This is going to be the kicker that changes the question for us. How much is in her account after 3.5 years? Alrighty, let's take a look. We need to use our formula, A equals P, outside of 1 plus I to the power of n. But because our compounding period is not annual, we need to change both our I value and our n value. So our I value refers to the interest rate. Right now it's 4.5% per annum, but we're compounding monthly. So we actually need to divide by 12 to turn it into a monthly one from a yearly. So 4.5 divided by 12, and that would be per month at that stage. So my calculator tells me 4.5 divided by 12 is 0.375. And that's still a percentage. Okay, because I haven't divided by 100 yet to turn it into a decimal. That's what I'm going to do now. So as a decimal, 0.375% is actually 0.00375. Okay, and that's per month. Now my n value refers to the number of compounding periods which occur. So I'm working with 3.5 years here, but I am compounding monthly. So I need to think about how many months occur in 3.5 years. So obviously, if I had 1 year, I would times by 12, and it would be 12 months occur in 1 year. So that means I can get 3.5 years and times by 12, and that will tell me how many months occur in 3.5 years. And the answer is 42 months occur in 3.5 years. Alrighty, so now I've got my I value that I actually will substitute in and my n value that I'll actually substitute in. I first had to make sure they were in the correct time period of months. So now let's substitute into our formula over here. Our p-value is 50,000. That's the amount that was originally invested. And now our I value is 0.00375. And our n value is 42. Okay, so you'll notice because this is compounding monthly, my n value is a lot higher than the previous question because we're talking about how many months occur in that time period, not how many years. See, our n value here was only 3, but now it's 42. But that won't make our answer a lot larger because also our interest rate is a lot smaller because now it's a monthly interest rate. So now let's take a look at our answer. It's 50,000 outside of 1 plus 0.00375, all to the power of 42. And the answer is $58,511.80. So I hope that's been enough to show you guys how to work through these exercise questions. We have sort of 2 different kinds of questions to think about. We have when our compounding period is annually, and we can just use the formula in a really straightforward way then. But then we also have non-annual compounding periods, so monthly, weekly, fortnightly. And in those cases, we need to be careful that our I value and our n value match the time period in question. Thank you, Year 10.